Hello there and welcome to Science for Sleep. I'm glad you found your way here. Maybe it's late where you are, maybe it's just quiet, maybe you're winding down, eyes heavy, blankets pulled close, and the rest of the world is finally gently falling away. Maybe you're not trying to sleep at all, just looking for something soft, something slow, something to follow in the dark. Wherever you are right now, this space is for you. A still, steady place where your thoughts can drift like leaves in slow water. We don't need to get anywhere. There's no quiz at the end, just ideas, explored softly, like a long walk without a destination. Tonight we're going to talk about time, not in the usual sense, not alarms or appointments or lost hours, but time as something more mysterious, more slippery. Something that might not be the same everywhere. Something that might, just maybe, be different in other universes entirely. I know that sounds enormous. Universes, plural, as in more than the one we live in? Yes, that idea. We'll go there, but we'll go there slowly, because the moment you bring up other universes, other realities, other versions of now, it's easy to get lost in big ideas. This isn't about getting lost though. It's about getting curious at a pace you can fall asleep to. So before we get pulled into that idea, let me ask you something simple. What time is it where you are? Not just the number on the clock, but the feeling. Is it that strange time between midnight and morning? Is the light still just barely on, flickering like thoughts that haven't quite settled yet? Is your room still warm from the day, or already cooled by the breath of night? Sometimes time feels like it's passing. Sometimes it feels like it's standing still. Sometimes an hour takes a second, and sometimes a second takes forever. We all know that feeling, even if we don't know why it happens. If this kind of slow wandering helps you unwind, helps your thoughts untangle, I'd love it if you gave this video a quiet little like. Maybe even subscribed if you'd like more sleepy science stories like this one. And if you're listening from somewhere special, a city just falling asleep, a tiny town no one's ever heard of, a chair that creaks when the wind hits the window just right, I'd love to know. The comments below are a little constellation of listeners all over the world. It's always lovely to see where you're tuning in from. Now then, let's take a breath. Nothing fancy. Just in and out. And again, just to let the day fall a little further away. You don't need to know anything before we start. You don't need to remember it later. But I'll tell you a story anyway. Let's talk about time. We tend to treat time as something steady. A line that moves forward. A ruler with ticks. We live our lives between those ticks. Birthdays, mornings, afternoons, deadlines, wake-up calls. We tell ourselves that time is flowing from the past to the present to the future. But is that how it really works? That's the question scientists have asked for centuries, and more recently they've started asking a weirder version of it. Does time have to flow that way? Does it even have to flow at all? Could it, somewhere else, in some other pocket of reality, move differently? Maybe not even forward, maybe sideways, maybe in loops, maybe not at all. And suddenly, we're not just talking about time anymore. We're talking about universes, other universes. Because the moment we start imagining time flowing differently, we're asking what kind of place time is inside of. And our universe, this one, has rules. Rules we think we understand. But if there are other universes, there's no reason to assume they follow the same ones. But let's not skip ahead too quickly. We've got time, quite literally. There's something strange about how we experience it. Right now, for example, you're listening to this in a sequence, one word after the next, 1 second after another. That's the only way we can experience time, through the lens of now. You remember what just happened. You anticipate what might come, but the only thing you ever truly touch is the present. The question is that just how we experience time, Or is that how time actually works? For most of history, people thought of time as absolute, a universal metronome ticking the same everywhere, no matter where you were or how fast you were moving. But that idea didn't survive the 20th century. In 1905, a young patent clerk named Albert Einstein proposed something that changed everything. He said that time isn't the same for everyone, that it flows differently depending on how fast you're moving, that clocks in motion tick more slowly than clocks at rest. This was the heart of his theory of special relativity, and later he expanded it, showing that time also slows down near heavy objects. That's general relativity. In other words, gravity bends not just space but time itself. If you flew into orbit with a very precise clock and someone else stayed behind on Earth with an identical one, when you came back, your clocks would not match. You would have aged slightly less. And this isn't just theory, we've tested it. GPS satellites have to account for these differences constantly. If they didn't, your maps would send you into the ocean. So time already behaves strangely, even in our own universe, and that's before we start imagining others. But why would we even think other universes might exist? It's not just science fiction, it's actually a serious idea in physics, one that comes out of a few different theories. The multiverse, it sounds dramatic, like a superhero plot. But in science, it just means maybe there are other regions of reality with different rules. There are a few reasons scientists take this idea seriously. One of them comes from a theory called cosmic inflation. Right after the Big Bang, the universe expanded faster than the speed of light. This inflation smoothed everything out, spread matter across space, and gave us the universe we see today. But inflation might not have stopped everywhere. It might still be happening, in pockets, like bubbles forming in a boiling pot. Each bubble could be its own universe. Some might be wildly different, others just slightly off. Ours is just one of many. And here's the weird part. In some of those other universes, time might not flow the way it does here. That's not just speculation. It's a possibility that emerges from the math. If the constants of nature were just a little different, the strength of gravity, the charge of an electron, the rate of expansion, time itself could behave differently. But what does differently even mean? That's where it gets tricky. Because even in our own universe, we don't fully understand time. Is it fundamental, something that just exists? Or is it emergent, something that arises from deeper physics we haven't grasped yet? Some physicists think that time might not even be real in the way we think it is. That at the most fundamental level there's no past or future. Just a giant block of reality where all moments exist at once, and our experience of moving through time is just a trick of consciousness, like watching a film one frame at a time when the whole reel already exists. In other words, what we call time might just be the way we're built to perceive a much stranger reality. If that's true, if time is not a basic feature of the universe, but a kind of mental overlay, then it could easily look very different somewhere else. But let's bring it back down for a moment. Right now, wherever you are, time feels like it's moving. You're breathing. Your heart is beating. The words you hear are unfolding in order. There's a rhythm, a flow. That feeling is real. But is it the only way time can be felt? Let's imagine. Not wild speculation, just gentle thought. Imagine a universe where time is not a line but a spiral, where every moment repeats, not identically but closely. A rhythm that loops, not forever but for a while, then changes, a dance of recurrence. Or imagine a universe where time moves in two directions, forward and sideways, where events don't just cause future events but neighbouring ones, a branching, tangled forest of cause and effect, not a single trail. It's not that these ideas are definitely real, but they aren't nonsense either. They're questions physicists are trying to answer. Because when we study the equations that describe reality, time isn't always special. It doesn't always point one way. Many fundamental equations work just as well backward as forward. That's deeply unsettling. because it suggests that time's arrow, the thing that gives it direction, might not be a rule at all. It might just be a tendency. So what makes time go forward? The best answer we have is something called entropy. It's a measure of disorder, and in our universe, entropy increases. Systems move from order to chaos. Ice melts, buildings crumble, eggs break, not the other way around. This gives time a direction, a before and after, but again, that's how it works here, in this universe. If a universe had different rules for entropy, time might flow differently. Or not at all. You might be wondering how we could ever know. If these other universes exist, if their time is different, if they're even real. And the truth is, we might never know for sure. They could be forever out of reach, hidden beyond our observable horizon, untouchable, unknowable. But that doesn't mean the question isn't worth asking. Because sometimes, just wondering changes how we see the world we already live in. And right now, in this moment, you are moving through time in a very specific way. Your body aging, your cells changing, your thoughts unfolding in sequence. But maybe, just maybe, in some distant or neighbouring universe, something else is happening. A different kind of unfolding, a different rhythm, a different experience of now. What is time, really? It's the kind of question that sounds simple until you actually try to answer it. You might look at a clock and think, that's time. Or maybe you think of your schedule, or how long it's been since lunch, or how many years have passed since a certain memory. You might even think of wrinkles or sunsets, or the sound of someone's voice changing over the years. These are all things we associate with time. But none of them explain what it is. We treat time like a background setting, something that's just always there. Everything we do takes time. Every thought we have, every motion, every breath, every change, it all happens over time. But even though we depend on it completely, we don't really know what we're depending on. That's not just a problem for people lying in bed wondering about big things. It's a problem for scientists too. Time is one of the most basic ingredients in every scientific theory, every equation. And yet, it's also one of the most mysterious. When you really look at it, time doesn't behave the way we think it does. It doesn't act like a simple ticking metronome. In fact, the more we've learned about the universe, the stranger time has become. The deeper we dig, the more it slips through our fingers. At its most basic level, time seems to be tied to change. When something changes, we say time has passed. When nothing changes, it feels like time has stopped. That's how our brains register it. And that makes sense. Our memories are a record of change. Without memory, we wouldn't be able to feel the flow of time at all. But there's a difference between the way we experience time and the way time behaves in the physical world. To explore that difference, scientists have tried to define time mathematically, to describe it in a way that doesn't depend on feelings or perception. In physics, time is usually treated as a dimension, like space. Just as you can move through space by changing your position, you move through time just by existing. You're always moving through it, 1 second at a time, always forward, at least that's how it feels. But when you look at the equations that describe how things move, time isn't treated as special. In most fundamental laws of physics, time could just as easily run backward. If you watch 2 billiard balls collide, the motion makes sense whether you play the video forward or in reverse. The math doesn't care. That's strange. Because in real life, we never see broken glasses leap back onto tables. We never see people getting younger. We never see smoke returning to a candle. So something must be different about the direction we experience. One explanation is entropy, the idea that systems tend to go from order to disorder. A deck of cards starts out organised, and when you shuffle it, it gets messier. A hot cup of tea cools down over time, the heat spreads out, that's entropy increasing. And the second law of thermodynamics says that entropy always increases in a closed system. That's why you don't see the mess unmess itself. Some scientists think this increase in entropy is the real reason time seems to move in one direction. that what we call the arrow of time isn't a property of time itself, but a result of entropy increasing. If entropy stayed the same, maybe time wouldn't feel like it was moving forward. But that only pushes the mystery back one step. Why does entropy increase? And why did it start low in the first place? No one really knows. There's also the question of how time interacts with space. In Einstein's theory of relativity, time and space are woven together into a single thing, spacetime. Instead of thinking of the universe as a stage where things happen in space and then in time, you think of it as a four-dimensional fabric, where positions in space and positions in time are just points on the same map. That sounds abstract, but it has real consequences. It means that time can be bent, it can be stretched, it can be experienced differently depending on how fast you're moving or how close you are to a massive object. This is not just theory. We've measured it. When astronauts orbit Earth in high-speed spacecraft, time moves more slowly for them than it does for people on the ground. When you stand on the surface of Earth, time moves more slowly than it does in orbit because you're closer to Earth's mass. The differences are small, fractions of a second, but they're real. GPS satellites have to constantly correct for this difference, or else your phone's location would drift by miles every day. All of this suggests that time is not absolute. It's not the same everywhere. It depends on context. That already breaks the idea that there's a single, universal now that everyone shares. Think about that for a second. We often assume that there's one true present moment, a now that everyone in the universe experiences together. But relativity says otherwise. It says that what you call now might not be the same as what someone else calls now, especially if they're moving quickly or are far away in a strong gravitational field. That doesn't just apply to hypothetical aliens. It applies to clocks on mountaintops versus clocks at sea level. It applies to you versus your own GPS. We're all moving through slightly different versions of now. So what is time really? Is it just a measure of change? Is it a dimension like space? Is it a product of entropy? Or is it something even deeper? Something we haven't yet fully defined? Some physicists think time might not be fundamental at all. They argue that what we experience as time might emerge from other processes, just like temperature emerges from the motion of molecules. There's no single molecule that has temperature, but when you put enough of them together and they start moving, you get something new. Time, in this view, might be like that. Not a basic ingredient of the universe, but a side effect of other things happening. This idea is hard to test, but it opens the door to something else. If time is emergent, then it might emerge differently in different contexts. In other words, other universes, if they exist, might have different kinds of time, or none at all. In fact, some versions of string theory, a framework for unifying all known forces in physics, predict universes with more than one time dimension. Not just forward and back, but sideways in time or up and down. That sounds impossible to imagine, but mathematically it's allowed. And if it's allowed, nature might try it somewhere. There's also the question of how time began. In our universe, time seems to have started with the Big Bang, or at least that's where our current physics breaks down. Before that, we don't know what time was, or whether it existed at all. So we find ourselves in a strange position. Time is everywhere. Everything we know depends on it. But the more closely we look, the less certain we are about what it actually is. You can't touch time, you can't bottle it. You can't slow it down or speed it up, at least not consciously. But you can feel it. You feel it when you age. You feel it when you wait. You feel it when you remember something from long ago. You feel it slipping past when you're lying in the dark listening to your own breathing. But those feelings don't explain what time really is. They just show how it touches us. And maybe that's why the question matters so much. Because even if we can't define time perfectly, we're made of it. We live inside it. And if it can be different somewhere else, that tells us something strange about what we are. We're not just creatures of flesh and thought. We're creatures of time, bound to its flow, aware of its passing, confused by its rules. The next time you wonder what day it is, or how fast the weekend went by, or why a single hour can feel like a lifetime, remember that you're not alone. Scientists with the most powerful tools in the world are wondering the same thing. What is this thing we call time? Why does it seem to move in one direction, and could it behave differently under other rules? Maybe, in some universe, it does. But to understand that possibility, we first have to ask whether time is even something that flows, or if that's just the way we experience it. It's easy to think of time as something that ticks, something mechanical, something regular, like the second hand of a clock moving forward, one notch at a time. But when you sit with the idea a little longer, it starts to feel less obvious. That ticking sound we all recognise. It's not time itself. It's just a machine we built to track time. A rhythm we invented, not one that was there before us. The clock doesn't know anything. It doesn't understand what it's measuring. It just moves in fixed steps because we told it to. And that brings up something strange. If all the tools we use to measure time are just human creations, how can we be sure that what they show us is what time really is? You look at a clock and it says 9. You look again and it says 9:01. Something has changed. Something has moved forward. But all the clock did was shift its hands. You still have to bring the meaning. You're the one who says that a minute passed. The clock just turned. So we're left wondering whether time is something that actually moves, or whether we're just moving through something fixed. Are we riding a river with the present moment pushing us along? Or are we walking across a landscape that's already there, with past, present and future all existing at once? One of the strangest ideas in physics is that time might not flow at all, that it's not something that moves forward, that instead, every moment, every second, every event just exists, all at once, forever. And the only reason we feel motion is because of how our brains work. Like a spotlight moving along a film strip, the whole movie is already made, but we only experience one frame at a time. This way of thinking is called the block universe model. It comes from relativity. The idea is that all points in time, not just the ones we call now, are equally real. The past hasn't disappeared. The future isn't waiting to be made. It's all just there, fixed, permanent. A four-dimensional structure with time as one of its axes. It's a difficult thing to imagine. We're so used to thinking of time as something that flows like a stream. But physics doesn't require it to flow. Nothing in Einstein's equation says that the future needs to be created moment by moment. That's something we project onto the world. From our perspective, there's always a difference between before and after, between cause and effect. You light a candle, and then it glows. You say something, and then someone responds. You touch a cup, and then you feel the warmth. We never see the order reversed, but just because we experience time this way doesn't mean it actually works like that. A useful analogy is space. If you walk from one room to another, your position changes. You're in a new place, but the room you left still exists. You're just not in it anymore. In the block universe model, time works the same way. You leave a moment behind, but that moment doesn't vanish. You're just not in it. This model has some strange consequences. It means that everything that's ever happened, and everything that ever will, already exists. Your birth, your best memory, your last heartbeat. All of it is in the structure of space-time, not waiting to happen, just there. But if time doesn't flow, then why does it feel like it does? That's where consciousness comes in. Some scientists think that what we experience as the passage of time is just a result of how we process information, that we remember the past and not the future because of how our brains are wired, not because of something built into the universe. Your brain collects data, compares it, builds stories, makes predictions. It strings events together. It looks for order. That's useful for survival. If we didn't experience time as moving, it would be hard to make decisions, hard to learn from mistakes, hard to even understand cause and effect. So maybe the flow of time is just a feature of how consciousness works, not a property of the universe. That would explain why our experience of time is so inconsistent. Why 5 minutes can feel like an hour. Why an hour can vanish in a moment. Why some memories feel closer than others, no matter how far apart they are. It would also explain why we can't remember the future. If time is already there, why don't we see what's coming? Some theories suggest that we only remember the past because entropy increases in that direction. The idea is that memory, like everything else, follows the arrow of disorder. You can remember a broken plate because the image of it stayed in your brain, but you can't remember the future version of that plate because those patterns haven't formed yet in your mind. That explanation doesn't feel very satisfying, but it's consistent with the math, and it raises an odd thought. If time doesn't flow, and all moments already exist, then maybe time is more like space than we realise. Maybe we're just walking a path through a landscape that never changes, only our position does. This idea isn't new. Philosophers have wondered about it for centuries, but now physicists are taking it seriously too. Some even think that we might one day find a way to test it. For example, if the block universe model is true, it might change how we think about causality, about free will, about memory. It might even change how we approach things like quantum mechanics, where particles seem to exist in multiple states until observed. Because if all events are fixed, maybe observation isn't changing anything. Maybe it's just telling us where we are in the structure. It's hard to accept. We like to think that the future is open, that choices matter, that anything can happen, and maybe that's still true in some way. But if time doesn't flow, if the ticking of the clock is just a perception, then our place in the universe might be more static than we thought. Still, whether or not the block universe is real, the illusion of time's passage is incredibly strong. We feel it, deeply, and maybe that's what matters most in the end. After all, you're here now, listening, and the moment before this one is already gone. The next one is just arriving. That rhythm, that unfolding, it feels like motion. It feels like progress. But the question we're asking is whether that feeling reflects what time really is, or whether it's just something we invented to make sense of our lives. Because if it is just an illusion, that opens up something even more surprising. It means time could look different somewhere else, that the way we experience past, present and future might not be the only way. That's not science fiction, that's physics. And it brings us back to a strange idea. If time is not universal, and if its flow is not real, then we have to ask what would happen in a universe where those rules were different. You've probably heard the phrase, time is relative. It's repeated so often now that it almost feels like a cliché. But for something so commonly said, it's rarely explained in a way that feels real. You hear it, you nod, and you move on. But what does it actually mean? How can time, something we usually think of as constant, be flexible? To get there, you have to start with gravity. Not in the falling down sense, but in the space-bending, time-stretching way. Gravity is the key to understanding how seconds change depending on where you are and what's around you. Most of us grow up learning that gravity pulls. It keeps you on the ground. It makes things fall. It's what holds the planets in orbit. That's not wrong, but it's also not the full story. There's a deeper explanation, and it comes from Einstein. Einstein's general theory of relativity changed the way we understand gravity. Instead of imagining it as a force pulling objects together across distance, he described it as something else entirely. He said that mass bends the fabric of space and time, that space and time aren't separate things at all, but one connected fabric called Spacetime, and when you put something heavy into Spacetime, or like a planet or a star, that fabric curves. Everything that moves through Spacetime has to follow those curves, including you, including light, including time itself. That's where things get strange. If Spacetime is curved by mass, then time doesn't tick at the same rate everywhere. It stretches, it slows down in places where gravity is stronger, it speeds up in places where gravity is weaker. This isn't a metaphor, it's not theoretical, it's measurable. We've tested it. There are atomic clocks so precise that they can detect the difference in time between 2 points just a few feet apart, like the top of a mountain and sea level. Clocks closer to Earth's surface tick slightly more slowly than clocks higher up. The difference is tiny, but it's real, and over long periods it adds up. That's one of the reasons GPS satellites have to constantly adjust their timing. They're moving fast in orbit, and they're far from Earth's surface. That means two things are happening at once. Time is speeding up because they're in weaker gravity, and it's slowing down because of their velocity. Both effects come from relativity, and if the systems on those satellites didn't account for it, your navigation app wouldn't work, not even close. This is how we know that gravity really does bend our seconds. The closer you are to something massive, the slower your time runs. Not in a way you'd notice directly, so you won't feel it. But if someone else is farther away, their experience of time will be slightly different from yours. Imagine standing on the surface of a neutron star, one of the densest objects in the universe, while your friend hovers safely at a distance. To you, everything feels normal, but to your friend, you're moving in slow motion. Your voice is stretched, your clock ticks slowly. The difference in gravitational potential changes the rate at which time passes for each of you. Now take that difference and turn it up even further. Black holes are the extreme case. Their gravity is so intense that time near them slows dramatically. Get close enough to a black hole, just outside the event horizon, and a few minutes for you could mean years, even centuries for someone farther away. This isn't fantasy. It's what the equations say, and it's what we see when we look at objects orbiting these invisible giants. The idea of time stretching isn't just about clocks and measurements. It changes what we mean by now. If two people experience time differently depending on where they are and how they're moving, then their versions of now are not the same. One person's present could be another person's past or future. That's deeply counterintuitive, but it's baked into the structure of the universe. That means there's no absolute shared moment that exists everywhere at once. Every point in space has its own version of time, its own rhythm, its own flow. When we say gravity bends time, we're really saying that the structure of the universe changes how time behaves in different places. The universe doesn't run on one single clock. It runs on countless local clocks, all ticking at slightly different rates depending on their context. You live in that reality every day. You may not notice the difference, but it's there. Your feet experience time more slowly than your head. The particles deep inside Earth's core are aging just a tiny bit more slowly than the ones on the surface. Time is not uniform. It's curved. It's flexible. It follows the shape of the universe. This also means that when you look out into space, you're not just looking into distance, you're looking into time. The light from distant stars takes years, even millennia, to reach you. When you see a galaxy 1,000,000 light years away, you're seeing it as it was 1,000,000 years ago. That light travelled across curved space-time to reach you. It took a path shaped by the gravity of everything it passed along the way, so time and space are never separate. They bend together. They move together. They shape each other. This is why the idea of other universes becomes so interesting. Because if our own universe bends time based on gravity, then a different universe, with different rules, different matter, different geometry, could shape time in ways we can't even picture. Maybe in another universe, gravity is stronger. Time could move slower overall, or faster. Maybe there are regions with no gravity at all, just flat, empty space-time where time flows like a featureless current, never disturbed. Or maybe gravity behaves in ways we don't even have language for, just twisting time into forms we've never seen. It's also possible that in some universes time is not a smooth curve at all. Maybe it's broken into discrete chunks, more like frames in a film strip than a continuous flow. Some theories suggest that space-time might be quantized at very small scales, meaning there could be a smallest possible unit of time. If that's true, then what feels smooth to us might actually be made of tiny steps we're too big to notice. Gravity, in that case, wouldn't just bend time, it might decide how time exists at all. And if gravity can do that here, what might it do in other realms? We don't have the answers yet. But the fact that gravity changes time here, in ways we can measure, test, and rely on, tells us that time isn't some untouchable constant. It's part of the world. It's shaped by it. It reacts to it. And that means it's possible to imagine a universe where time has a different shape entirely. But to think about that, we have to ask a new question. If time can bend, and if the past and future are shaped by where and when we are, then what happens when we step outside our own universe in theory? What might time feel like in a place where gravity follows different rules? When we talk about time, it's natural to assume that it moves at a steady rate, that there's some built-in beat to the universe, a rhythm so consistent we rarely think to question it. Even with everything we've already said about time stretching and bending under the influence of gravity or speed, most of us still feel, deep down, that time is ticking along somewhere, silently and perfectly, in the background. That if we could step outside of everything, we'd still hear that ticking. But that idea doesn't hold up under closer inspection, because there's no universal clock, no central pulse, no baseline that applies to everyone, everywhere. Time is not a drumbeat echoing through the cosmos. It's more like texture, shaped by the environment, influenced by movement, dependent on position. So, if time can stretch and slow and warp, if it can act differently depending on gravity, speed and position, what would it be like in a place where all of that changed completely? What would it feel like to exist in a world where time moves not like the flow of water, but like honey, thick, slow, resistant to motion, a place where each moment drags behind you like something physical, something you can feel pressing on your skin. Not seconds ticking forward with ease, but time dragging, folding, hanging in the air like syrup. It's a strange thought, but not an impossible one, because what we call the speed of time isn't a constant experience. In our own universe, it already changes depending on where you are. The closer you get to a strong source of gravity, the slower time flows. So if you lived on a planet orbiting close to a massive star, or near the edge of a black hole, time for you would pass much more slowly than for someone far away. A minute on your planet might be an hour somewhere else, or a year, or 1,000 years. That's not fantasy. It's basic physics. Now stretch that further. Imagine a universe where everything, every structure, every field, every physical interaction is shaped around the idea of slowed time, where the baseline for how fast things happen is set much lower, where light takes longer to travel, where reactions take more time, where thought itself feels like it happens underwater. In that world, you wouldn't know anything was wrong. Your body would adapt to that pace. Your mind would match it. To you, it would feel normal. But if someone from our universe could step in and observe, they'd see everything moving at an impossibly slow crawl. A slow-motion version of life. Not broken, not damaged, just slowed. You wouldn't notice the difference because it would be consistent across everything you are. Your metabolism, your perception, your heartbeat, your breath, all would move in sync with the slower time of that world. It's not clear exactly how such a world would form, but it's possible depending on how the constants of physics are arranged. If the speed of light were lower, or if the gravitational field of the universe were more intense overall, or if the expansion rate of space were different, time itself could settle into a slower pace. That slowness would ripple through every process. Stars might burn longer. Galaxies might take more time to rotate. Particles might decay at different rates. Chemical bonds could form more reluctantly, requiring more time to stabilize. And what about consciousness? Would beings in a slow-time universe think more slowly? Possibly, but they wouldn't feel slow to themselves. The passage of thought would match the passage of time around them. They wouldn't think, "This is slow." They would simply experience the rhythm as normal. That part is hard for us to imagine, because we're locked into our pace. We're used to how long a second feels, but that's just biology. Evolution built us in this rhythm. It didn't have to. If we'd been shaped in a world where time moved more slowly, more like honey than wind, we would find that rhythm just as natural. Now imagine communication between two universes, one with time as we know it, and another with slow, syrupy time. How would those timelines ever align? A message sent from our universe might arrive too quickly to be processed, or too suddenly. Like dropping a stone into a pond covered in oil. The splash might take hours to ripple across. Likewise, if a message came from the slow time world into ours, it might feel almost still, delayed, compressed. We might miss it entirely, or mistake it for something static. The gap in perception could make two intelligent civilizations completely invisible to each other, not because they're far apart in space, but because their timelines don't match. That kind of mismatch would be just one outcome of a universe where time behaves differently. Other effects could be even stranger. Take light, for example. In our universe, it travels fast, about 300,000 kilometers per second. But light is still part of spacetime. If spacetime is thicker, slower, denser, like honey instead of air, light might crawl, it might trickle. A flash of light might take hours to move across a room. And yet, to the beings in that universe, it would still feel like a flash. Their definition of speed would be different. Not wrong, just slower. Temperature might behave differently too. If atomic motion is influenced by time's flow, then heat, which is just the movement of particles, might spread in slower waves. Cooling and heating would take more time. Physical sensations might linger. A change in pressure might fade over minutes instead of seconds. And what about life? Could biology emerge in a universe with slower time? It depends on what conditions support complexity. Time doesn't need to move quickly for life to evolve. It just needs to be stable, consistent, and long-lasting. If the physical rules support energy flow, chemistry, replication, and memory, then something like life might still take shape, even if its heartbeat is 1,000,000 times slower than ours. We tend to associate speed with complexity, but that's not a requirement. A slow universe might be just as rich, just as layered, just as intelligent, only on a timescale that makes our perception seem like flickering static. To them, we might be barely visible, a flash in the dark. It's possible that these timelines could never interact. Not because of distance, but because of tempo. Like trying to have a conversation between a hummingbird and a glacier. The scales are too different. The signals don't match. But just thinking about that, about worlds where time is slow, where motion is dense, where thought is stretched, it forces us to let go of the idea that our way is the only way. It reminds us that time is not a rule, it's a condition, a setting, something shaped by the universe, not something that shapes it. And if it's shaped differently elsewhere, then everything, life, energy, meaning, might look unfamiliar too. None of this proves those slow-time universes exist, but we don't need proof to wonder. The possibility is enough to ask what we might learn just from the question. And the question leads naturally to another. If time can stretch like honey in one universe, could it contract like lightning in another? Could there be a universe where everything happens fast, too short-lived for us to even see? If we've learned anything so far, it's that time isn't what we thought it was. It doesn't flow the same everywhere. It stretches, slows, speeds up and bends, all depending on where you are and what's around you. That alone is enough to unsettle the way we think about reality. But it's also what prepares us for the next step, because once you understand that time isn't fixed, once you see that it's shaped by context, by environment, by structure, then it's only natural to ask what might happen if the entire structure changed. Not just gravity, not just motion, not just entropy, but the whole container itself, the space in which the rules are written, the universe. This is where we start to leave the comfort of what we can see and test. But we don't have to leave reason behind. This isn't fantasy. It's a carefully shaped possibility. And like most good questions in science, it started because we found a crack in what we already thought we understood. The idea of a universe sounds complete. It sounds like the final layer. But when physicists started modelling the very early stages of our universe, the first fractions of a second after the Big Bang, they ran into something strange. The math suggested that expansion didn't happen evenly. It wasn't like a balloon inflating. It was more like rapid, chaotic blooming. Regions of space expanded at different rates, separated from each other, isolated before they had a chance to connect. In that picture, our universe is just one region, one bubble among many. These other regions, the ones that branched off, expanded differently, or formed under other starting conditions, are what we call the multiverse. Not as a storytelling device, but as a real, if still unconfirmed, consequence of our best cosmological models. There isn't one version of the multiverse. There are several ideas that point toward it. Some come from inflation theory, others from string theory, which suggests that there may be many possible ways to shape the laws of physics. Each way could lead to its own kind of universe, with different forces, particles, or even numbers of dimensions. We're not going to dive into the full weight of those theories here. Instead, we're going to follow one idea gently, that there could be other universes and that each of them could contain a different kind of time, not just a different speed, not just a longer or shorter day, but a fundamentally different structure of time, one shaped by a different beginning. To even begin thinking about this, we have to understand what it means to be beyond our universe. That word makes it sound like there's a place you can go, some direction you can point in, and eventually cross over into something else. But space doesn't work that way. Our universe doesn't sit inside something larger. It's not expanding into an empty container. It's not a dot growing inside a whiteboard. It's everything. It's space itself stretching. It doesn't expand into anything, it just expands. So when we talk about other universes, we don't mean ones located somewhere far away in space. We mean something else entirely. We mean isolated regions of reality with no causal connection to ours. Bubbles of space-time cut off from each other, each with its own version of physics. Maybe they're next to each other in some higher dimensional space. Maybe they're part of a repeating cycle, forming and collapsing over and over again. Maybe they're spun off by quantum fluctuations. Maybe they exist as mathematical possibilities that are just as real as our own. We don't know. But the reason we're looking here, the reason we're even daring to ask what time might be like beyond our universe, is that everything we've seen about our own shows us how flexible time already is. So if other universes exist, we have no reason to assume time would work the same way inside them. In some of those universes, time might never have started. There might be no moment of creation, no Big Bang, no arrow pointing forward, just a static field of existence where everything is fixed and unchanging. Not because time has stopped, but because it never began. Or maybe time exists there, but it runs in more than one direction. Imagine a universe where time isn't a line but a plane, something with two axes. In that space, events could spread out in two dimensions, not just forward and backward. Causality might work in strange loops. The idea of past and future might not exist at all. And what about time without change? Could there be a universe where time passes but nothing ever happens? That sounds paradoxical, but it's worth asking, because time, at least as we understand it, is tied to change. If nothing changes, how can you tell time is passing? But if the fundamental structure of a universe includes a ticking parameter, a variable that keeps increasing, then time could still be there, even if no events ever mark its movement. It would be like a frozen film with a running clock. Nothing ever moves, but the time code keeps counting up. And then there's the possibility of time running backward. Not just in isolated systems, which we already know can happen under very specific rules, but as a default, A whole universe where entropy decreases, where order increases over time, where everything starts scattered and slowly arranges itself. In that universe, if consciousness evolved, would they remember the future and forget the past? We don't know, but the thought is worth sitting with. Because these other universes, if they exist, would not just be strange copies of our own. They wouldn't just be versions with green skies or heavier gravity. They would be entirely different frameworks, not just different stories, different rules for how stories work, different ways to structure moments. And if time is flexible in the way relativity already tells us, then it's completely reasonable to imagine that time itself might take on unfamiliar shapes in places with unfamiliar rules. We may never reach those places. They might be forever separated from us by expanding space. We might never receive a signal, never build a bridge, never glimpse them directly. But we can model them. We can think about them. We can test the edges of our own universe and look for signs, tiny patterns, distortions, or quantum anomalies that suggest we're not alone in the broader structure of reality. That doesn't mean proof is around the corner, but even the possibility changes how we see ourselves. It reminds us that the rules we live by might not be universal, that the flow of time we feel every second might be a local property, not a law of everything, but a regional effect. And just like local customs vary across towns, perhaps time does too, across realities. So if we could peek beyond our universe, we might not find a place that feels like space. We might not find stars or gravity or light. We might find a kind of logic that doesn't line up with ours. We might find time that loops or skips or diffuses. Or maybe time is the same everywhere. Maybe it's deeper than any rule. Maybe it's the one constant that even universes can't rewrite. We don't know, but asking helps. And the more we understand how time behaves here, the better we can imagine what it might look like. There. We've been talking about time, how it bends, how it stretches, how it behaves strangely depending on where you are. And with each step, we've gotten a little farther from the familiar, a little closer to something that sounds abstract, but is really just another way of asking, could everything be different, somewhere else? It's one thing to imagine time moving slower near a black hole. That's strange, but we can measure it. We can test it. But it's another thing entirely to ask what would happen if the whole framework changed. If the rules that shape our reality, the ones that let time exist in the first place, were replaced with something else. And that brings us to the question people often hesitate to say out loud. What if other universes exist? It doesn't feel like the kind of question we're supposed to ask seriously. It sounds like something from science fiction, a plot device, a conversation starter at 2 a.m. But the more we learn about our own universe, the more it seems like that question is not only worth asking, it might be impossible to avoid. To get there, let's take a slow step back. You live in a universe with certain ingredients, certain numbers, constants, forces, rules. The speed of light has a value, gravity has a strength, particles have mass. The universe expands at a measurable rate. These aren't just details, they're the reason we exist. If even one of those numbers was slightly different, stars might not form, atoms might not bind, life, as we understand it, might not be possible. That observation, the fact that the universe seems surprisingly tuned for complexity, has bothered physicists for a long time. Not because it's mystical, but because it's statistically odd. Why this set of rules? Why this exact balance? There are a few ways to approach that question. One way is to say it's a coincidence. Another is to look for a deeper explanation, some rule or equation that forces the universe to be this way and no other. But a third possibility is that our universe is just one among many, not special, not selected, just one version. That idea is called the multiverse. The word sounds dramatic, but the meaning is quiet. It doesn't imply magic or fantasy. It just means that what we call the universe, everything we can see or measure, might be a local patch of a much larger reality. a bigger system, filled with regions that don't connect to each other, don't follow the same rules, and may never be observable from within our own. So when we ask, what if other universes exist? We're not imagining parallel versions of ourselves. We're asking whether space, time, and physics themselves can take other forms, not elsewhere in space, but elsewhere in structure. There are a few places where this idea shows up. One is in cosmic inflation. That's the theory that right after the Big Bang, space expanded incredibly quickly, faster than the speed of light. Not objects moving through space, but space itself stretching. That kind of expansion would have been chaotic. Different regions could have stretched at different rates, disconnected before they could influence each other. In that scenario, our observable universe is just one pocket, one bubble in a vast sea. Each bubble would be its own universe, isolated, self-contained. The laws of physics might be slightly different in each one, the constants might vary, and in some bubbles those changes might be so extreme that time itself behaves differently. Another version comes from string theory, a mathematical attempt to unify all the forces in the universe. String theory allows for many possible configurations of reality, different ways to shape space, different patterns of energy, different arrangements of particles, and each of those configurations could give rise to its own version of a universe. That collection of possible realities is called the landscape, and if the universe is capable of exploring that landscape, it might try all the possibilities. Each possibility becomes its own universe. Ours is just one of them. There's also the many worlds interpretation of quantum mechanics. In that picture, every possible outcome of every quantum event actually happens. Not metaphorically, but physically. The universe splits, branches. Each possibility becomes real in its own timeline. That's not the same as the inflationary multiverse, but it leads to a similar question. Are we living in one thread among countless others? No matter which version you follow, the idea is the same at its core, that what we call the universe may not be the whole story, that it may be one piece of a larger pattern, one rulebook among many. And if that's true, then time, the thing we've been exploring so slowly, might not be a universal concept at all. We've already seen that even within our own universe, time is flexible. It stretches under gravity. It flows differently depending on motion. It's not absolute. So what happens when we step beyond that? When the rules that define gravity, or motion, or causality are replaced with different ones? Maybe there are universes where time is reversible by default, where cause and effect can switch places, where actions don't follow sequences in the way we expect. Maybe there are universes where time doesn't exist at all, where existence is frozen, or timeless, or shaped by something we can't even recognize as time. Or maybe there are universes with multiple time dimensions, more than one way for events to unfold. In that case, time might be something you can steer. Not a path you follow, but a field you can turn in. These are not wild guesses. They're the kinds of structures that emerge from the math when physicists try to describe reality at its most basic level. And while we don't know if these universes are real, the logic that leads to them is grounded. You might wonder what difference it makes. If we can't visit these other universes, if we can't communicate with them or observe them, why ask what they're like? The answer depends on how you see science. For some, it's only about what can be tested. But for others, science also includes structured imagination, not fantasy, but careful reasoning about what might be possible based on what we already know. By thinking about other universes, we learn more about our own. We see what's fixed and what's flexible. We see what's required and what's optional. We find out which parts of our reality are fundamental and which are just local conditions. And when it comes to time, that matters more than almost anything else. Because time is the lens through which we experience everything. Every thought, every movement, every breath. They all arrive through the structure of time. So if time can change, then our experience, our most basic sense of being, could change too. In a different universe, consciousness might feel completely different. Thought might not follow the same path. Memory might not work. Perception might not unfold in the same direction. And that makes the question of other universes feel less abstract. It's not just about space. It's not just about rules. It's about the texture of experience itself. What is it like to be alive under a different kind of time? Maybe no one knows. Maybe no one ever will. But maybe somewhere, that kind of experience is already happening. Quietly, in parallel, in another structure of reality, following a different rhythm. It's easy to hear the word multiverse and picture something dramatic, infinite versions of Earth, endless copies of you making different choices, branching timelines and doppelgangers living parallel lives. But that version, the one shaped by stories and science fiction, is just one interpretation. The real idea, the one proposed by physicists and cosmologists, is both simpler and more difficult. It isn't about dramatic mirrors, it's about possibility. And it all comes back to how space-time and rules might be different somewhere else. At its core, the word multiverse doesn't mean copies. It doesn't mean repetition. It means structure beyond what we can see. Not a trick, not a fantasy, just a natural consequence of how certain models explain the origin of our universe. There's a reason this matters when we talk about time. Because once you accept that our version of time, our ticking, bending, stretching time, is shaped by the specific rules of our own universe, then the next question is obvious. What if the rules change? And if the rules can change, how many other ways might time be arranged? That's where the multiverse enters, not as decoration, not as speculation, but as a serious framework for considering all possible versions of physical law and how each one might shape a completely different experience of time. Let's step through a few of the models slowly. The first is eternal inflation. We touched on it earlier. It comes from trying to understand what happened in the earliest moments after the Big Bang, a period when space itself expanded faster than the speed of light. That rapid expansion didn't happen all at once. It happened unevenly, unpredictably in patches. And the theory says it never really stopped. It's still going, somewhere beyond what we can see. The space we live in, everything we can observe, is just one pocket where inflation slowed down, where matter cooled and coalesced. But in other pockets, inflation continued, forever. Each of those pockets becomes a universe. Each one has its own beginning, its own contents, its own shape, and potentially its own version of time. In some of those universes, the constants might be slightly different. The speed of light might be lower, gravity might be weaker, time might tick more slowly, or faster, or not at all. None of those differences would require magic. They would simply be outcomes of a different balance of physics, different initial conditions, a different mix of ingredients. The second model comes from string theory. It says that the fundamental components of reality aren't particles, but tiny vibrating strings. And those strings can vibrate in many ways. Each vibration gives rise to different properties: mass, charge, interaction strength. The theory also predicts more dimensions than the 4 we're familiar with. Some of those dimensions are compact, curled up in ways we don't directly perceive. Because of all these variations, string theory allows for an enormous number of possible configurations of the universe. Some estimates say there could be 10⁻⁵00 different ways to set the constants and fields. Each combination produces a different kind of universe, a different way for matter, space, and time to exist. Not just variations on a theme, entirely distinct realities. The third version comes from quantum mechanics, specifically the many worlds interpretation. In this view, every quantum event doesn't just resolve into one outcome. Every possibility becomes real. The universe splits, not visibly, not explosively, quietly, constantly. Every time a particle can take multiple paths, it takes all of them, each one in a different branch of reality. If that's true, then our universe isn't a single thread. It's one of many threads, one of many outcomes. Each version could have its own timeline, its own history, even its own flow of time, depending on how deeply the branching affects the fundamental structure of spacetime. All three models, inflation, string theory, quantum branching, point to a wider reality, a structure that includes not just our universe, but many. That's what the multiverse really means. Not copies, not mirrors, just diversity. A space of possible universes, each shaped by different rules. And that's where the idea of infinity comes in. Because when you try to count the number of ways a universe can be arranged, the ways particles can combine, the ways fields can curve, the ways dimensions can fold, the number becomes hard to define. It might not be infinite in the literal sense, but it's big enough to behave like it is, big enough that trying to imagine it all becomes overwhelming. So instead of trying to picture it, we describe it softly. We call it the multiverse, a gentle word for something we can't really hold in our heads, a way to talk about the landscape of all possible realities without pretending we've seen the whole map. And when you look at that landscape, one thing becomes clear. Time, as we know it, is just one path through that space. It's not the only path. There could be other universes where time is faster, not just relatively, but fundamentally, where stars burn in moments, where thought is an instant, where nothing lasts longer than a blink, and yet everything still unfolds with meaning, because meaning adjusts to the scale. There could be universes where time doesn't move linearly, where instead of a single thread you have loops, branches, feedback, not random, not broken, just different. Structures that allow memory of the future, or multiple pasts feeding into a single present, or layers of time stacked like pages. There could be places where time moves sideways, where direction is not tied to before and after but to position, where you travel through time the way we walk through space, and where the very idea of aging or progress or story doesn't exist in the same way. These are not just dreams, they are mathematical consequences, allowed by the logic of our best theories, not required, but permitted. And if they're permitted, we have to consider them, because the more you understand how time behaves here, how fragile and conditional it is, the more you see that it doesn't have to be this way. The ticking clock we know might be one arrangement among countless others, and if there are countless other arrangements, then we are part of something far larger than we thought. That doesn't mean we'll ever visit those other universes, it doesn't mean we'll make contact. But it changes how we think about our own position. We're not the baseline, we're not the reference, we're one example. And when it comes to time, that realization is powerful. It frees us from assuming that our experience is the only kind. It opens space for imagination, not fantasy, but structured wonder. A way of asking what else might be possible. So the multiverse as an idea doesn't just change cosmology, it changes philosophy. It reminds us that the rules we follow are local, that even something as deep as time, something we feel in every moment, might be regional, temporary, specific. And once you let go of the idea that time is fixed, you can start to ask even deeper questions. What happens to stories in a universe without time? What happens to memory in a universe with multiple pasts? What happens to cause and effect if time flows in more than one direction? And what happens to identity, to experience, if the rhythm of time is completely unfamiliar? After everything we've considered, gravity, motion, the block universe, the multiverse, the next question seems obvious, almost childlike in its phrasing. If other universes exist, would time tick there the same way? It sounds simple, like a question you might ask without expecting an answer. But this is the kind of question physics is quietly circling around all the time. Not because we can answer it directly, but because the question itself tells us something about what time is. and what it's not. We already know that in our universe, time doesn't tick the same way everywhere. That alone breaks the idea of a universal rhythm. Time slows down near massive objects. It stretches when you accelerate. It's different depending on where you are and how fast you're moving. So if we already live in a universe where time doesn't tick the same everywhere, then stepping into another universe would only take that one step further. But to really ask if time would tick the same there, we have to get clear on what that ticking even means. We're used to thinking of time as a sequence of moments, 1 second, then another, a steady beat. We picture clocks, digital displays, or the sun rising and setting. But all of those are just measurements. They're tools. They don't tell us what time is. They just give us a way to mark its passing. The ticking we imagine, the rhythm of time, is just the way we've decided to count change. And that brings us back to a more fundamental view. Time is tied to change. If nothing changes, we can't tell if time is moving. So to even ask if time ticks the same in another universe, we have to ask how change works there. How motion, cause and effect operate. How systems evolve. Let's imagine a different universe. One where the constants of physics are altered. Not in wildly unrecognizable ways, but just slightly. Maybe gravity is stronger. Maybe the electromagnetic force is weaker. Maybe the speed of light is lower. In that universe, the way particles interact would be different. Stars might burn slower. Matter might form later. Processes would unfold at a different pace. Would time be ticking the same? From our perspective, no. The processes we associate with the passage of time, aging, motion, decay, fusion, would happen at a different rate. If we could somehow look in, we'd say time was moving more slowly. But from the inside, from the point of view of someone living in that universe, it would feel completely normal, because everything would scale together. Perception, chemistry, memory, light, gravity. They'd all sync to the same rhythm, just a different rhythm than ours. So maybe time is always local, always relative to the structure around it, but that's just one kind of difference. What if the structure is more deeply altered? What if that universe has more spatial dimensions, or fewer? What if time isn't a single axis, but two? What if it loops? These sound like strange features, but they're not forbidden by physics. Some models suggest that other configurations are mathematically consistent. A universe with two time dimensions might seem impossible to imagine, but only because we've never experienced it. In our world, time has direction. We move through it one way, always forward, always toward higher entropy. But that might not be a rule. It might be a result of the shape our universe took in the first moments after it began. In another universe, the shape could be different, and if the shape is different, time might not tick at all, or it might tick in patterns, or pulse, or fluctuate, or spiral. Would it still be time? That depends on what we mean by time. If time is defined as the parameter by which systems change, then yes, those patterns might still count, but they wouldn't feel like ticking. They wouldn't feel like seconds passing. They might not even feel like movement. They could feel like expansion, or contraction, or flickering, or something we don't have words for. And that brings us to a deeper problem. Our experience of time is built on a certain kind of biology. Our brains operate with memory. They process sequences. They compare states. That's what gives us the feeling of time passing. But in a different universe, under different conditions, consciousness itself might develop differently. It might not require memory, or it might experience information in a non-linear way. In that case, the experience of time wouldn't just be slower or faster. It would be unrecognizable. So when we ask whether time would tick the same in another universe, we're really asking two things at once. We're asking whether physical systems would evolve at the same rate, and we're asking whether experience would unfold in a similar way. And the answer to both might be no, not because time is broken there, but because time, as we know it, is only one way to arrange experience. There's another layer too. In our universe, time is connected to entropy, the tendency of systems to move from order to disorder. That increase in entropy gives time its direction. It's why we remember the past and not the future, why causes come before effects. But entropy, too, depends on the initial conditions of the universe. The reason we see entropy increasing is because it started low. Why did it start low? That's still an open question. But if another universe began in a high entropy state, or one with no clear entropy gradient at all, then time might not have a direction. There might be no clear distinction between past and future. Would events still happen? Maybe. But they wouldn't unfold along a single timeline. They might not progress. They might just exist, like static points, connected in a web instead of a line. From that perspective, asking if time ticks becomes meaningless. Ticking implies motion, sequence, progress. But if those ideas don't apply in that universe, then time wouldn't tick. It wouldn't even flow. It would just be. And yet, there might still be physics there, still be structure, still be relationships between events. Even without ticking, there could be rules. Would that still count as time? That depends on how broadly we're willing to define it. Maybe time isn't a ticking clock. Maybe it's just a way to describe the order, or even the coexistence, of different states. In that case, every universe might have something like time, but it wouldn't feel the same, it wouldn't move the same, and it wouldn't produce the same kind of experience. All of this brings us to a kind of quiet realization. Time is not one thing. It's not a universal standard. It's a set of relationships between matter and space, between memory and change, between cause and observation. When we ask whether time would tick the same in another universe, we're not asking about seconds. We're asking about the very shape of reality. In one universe, time might move in steps. In another, it might be continuous. In another, recursive. In another, absent. And in each case, the beings who exist within that universe would build their experience around what they have. They would think their version is normal, natural, obvious, just like we do. So maybe time doesn't tick the same in other universes, but maybe that's the wrong question. Maybe the better question is, how does change feel when the rules are different? Until now, we've mostly imagined time as a line. Sometimes that line stretches, sometimes it slows, sometimes it splits, but it's always moving forward. That's the version of time we live in, or at least the version we think we live in. A one-way flow, a sequence of moments that don't repeat. Each second leads to the next. The past becomes memory, the future remains unknown, and the present sits in between, always slipping away. But what if time isn't a line everywhere? What if, in some universes, or even in some corners of our own, time doesn't stretch, it curls? Instead of unrolling forward forever, what if it loops back onto itself? This is more than a thought experiment. It's an actual possibility within certain solutions of Einstein's equations. General relativity allows for structures called closed time-like curves. They're paths through space-time that circle back to the same point in time. You could, in theory, travel along one of these curves and end up at the moment you started. Not metaphorically, literally. This isn't science fiction, it's math. And under the right conditions, with the right configuration of mass and energy, those loops are allowed. They might not be easy to build, they might require exotic matter or negative energy, but they're not forbidden. That means our familiar concept of time moving only forward, always stretching away from the past, is just one possibility. There are others. Let's slow it down. Imagine a world where time doesn't extend infinitely into the future, but curls gently back toward the past. In that world, the timeline isn't a thread, it's a ring. Events repeat, not in the way a clock repeats its numbers, but literally, the same moments, the same decisions, the same patterns, again and again. This idea is unsettling to some. It brings up questions of free will, of repetition, of meaning, but it's not necessarily bleak. It's just different. In a curled timeline, nothing is lost. No moment slips away. Everything returns, over and over, permanently, eternally. But that leads to a question. Would anyone living inside such a loop know they were repeating? Not necessarily. If time loops, and you're inside that loop, your memory would reset each cycle. Your awareness would begin fresh every time. You wouldn't remember the previous loop because the previous version of you would dissolve at the end of the curve, replaced by a new one following the same path. So from your perspective, time would still feel linear. It would still feel like a forward flow, but outside the system, an observer could watch the same pattern happening again and again. You wouldn't experience the loop, you would be the loop. It's possible to construct spacetimes like this mathematically. One of the earliest examples was proposed by Kurt Gödel in 1949. He found a solution to Einstein's equations in which the universe rotates. That rotation twists spacetime in such a way that you can return to your own past, not by breaking the laws of physics, but by following the natural curve of time in that model. Other solutions include hypothetical structures like rotating cylinders, wormholes, and cosmic strings. These aren't confirmed to exist, but they're allowed by the math. They suggest that under the right conditions, spacetime could be twisted into a shape where the future and the past are not so easily separated. So what would life be like in a universe with curled timelines? It depends on the size of the loop. If the loop is incredibly long, billions of years, say, then beings living inside it might never notice. The universe would appear to expand, evolve, and cool. Stars would burn, galaxies would collide, civilizations would rise and fall. And then, eventually, the structure of space-time would bring everything back to its original state. The same Big Bang, the same expansion, the same history, again. That idea overlaps with the concept of a cyclic universe, one where the cosmos undergoes endless cycles of birth and rebirth, expansion followed by contraction, followed by another expansion. Each cycle could reset the conditions or carry over echoes of the last. Some cosmologists have explored this possibility seriously. The idea isn't that time literally loops in a small circle, but that the entire history of the universe forms a ring, immense but closed. In other versions, the loop could be much shorter. Seconds, minutes, hours, a closed circuit where events repeat almost instantly. Would that kind of loop allow for consciousness? Or for memory? Probably not in any familiar sense. But if consciousness were adapted to that environment, if it evolved within that loop, then it might experience time in a way we can't imagine. A sense of déjà vu so complete that it feels like permanence, a life lived within a single moment, stretched into endless recurrence. There's also the possibility of partial loops. Time might not curl completely. It might ripple or spiral or fold back in places. Some events might recur, others might not. The timeline might be smooth in some areas and looped in others. We already see something similar in systems that exhibit periodic behavior. Think of atoms vibrating, pendulums swinging, orbits repeating. These aren't time loops exactly, but they show how repetition can emerge naturally in a universe built on rules. In a more extreme case, time itself could be fundamentally looped, not just in local structures, but in its deepest geometry. Time might not have a beginning or an end, just endless curvature. No first moment, no final one, just motion around a circle, forever. This would change how we think about cause and effect. In our timeline, causes come before effects, but in a loop, those concepts lose their sequence. Every cause is also an effect. Every moment leads both forward and backward. There is no origin, just the ring. That idea is difficult to grasp because our brains are trained to think in lines. We're built to remember, to plan, to tell stories. All of those things rely on time moving in a single direction. But if you lived in a universe with curled time, your brain might evolve to think in loops, not remembering or anticipating, but sensing patterns, seeing recurrence, expecting return. In such a world, knowledge wouldn't be passed forward, it would be rediscovered. Over and over, art would echo itself, science would reinvent itself. Meaning would be found not in progress but in familiarity. The strangest part of all this is that we might already be inside a universe with some degree of curvature in time, and simply unable to detect it. If the loop is long enough, if the curve is subtle enough, we wouldn't feel it. Everything would seem linear. But eventually the path would curve back. There's no evidence that we live in such a loop, no measurement that confirms a curled timeline. But there's also no reason, based on current physics, to rule it out entirely. And if time can curl, even in theory, then we have to rethink what it means for time to move at all. Because in a loop, nothing is truly lost. Every event comes back. Every pattern returns. Every moment exists not once, but many times, or perhaps forever. So what happens to experience in a world like that? Does it matter that something has happened before if you can't remember it? Does repetition change the meaning of a moment? Or is every loop a chance to live again? These aren't just philosophical questions, they're structural. They ask what kind of time we might find in a universe with a different geometry. And once we accept that time might curl, that it might not always stretch endlessly forward, then we start to see other possibilities. Not just loops, but branches, crossings, braids, time as a network instead of a road. Once you've stepped into the idea that time doesn't have to be straight, doesn't have to move at the same pace, and doesn't even need to have a universal direction, it's not a huge leap to ask the next question. Not scientific exactly, but human. Could another version of you be living at a different hour? It's not the same as asking whether time moves differently in other universes. We've already walked through that, through bending seconds, curled timelines, and closed loops. This question is more personal. It takes what we've said about structure and asks what it would mean if you, or some version of you, were placed inside a different flow of time, a different rhythm, a different hour entirely. At first glance, it sounds like a story device, alternate realities, parallel lives. But under the surface, there's a real scientific and philosophical tension here, because what we call you is tightly bound to how you move through time, and if time can behave differently, then maybe identity isn't as fixed as it feels. Let's back up a little. In the most literal sense, your experience of time is completely dependent on where you are. We know this from relativity. Time ticks differently depending on altitude, gravity, velocity. Someone on the International Space Station orbiting Earth at high speed experiences time at a slightly different rate than someone standing still on the surface. That's not a theory, it's measured. If you lived your whole life at sea level and someone else lived it at the top of a mountain, your clocks would slowly disagree. Your experiences would diverge, not dramatically, but enough to notice over decades. That's just within one universe. Now imagine a version of you in a slightly altered universe. Maybe everything's the same atoms, same history, but the constants are just a little different. Time passes more slowly there, or more quickly. That version of you might look like you, speak like you, think like you, but the rate of experience would be out of sync. One of you might feel like they're an hour into the day, the other might feel like it's barely begun. But both are following the same script, just on different clocks. Would that make them different people? Or is it still you, just stretched across uneven time? This is more than an abstract question. It touches on how we define the self. If your thoughts, memories, emotions, if all of those things are shaped by the pace of your reality, then altering the pace might change what you means. There's also the matter of branching. In the many worlds interpretation of quantum mechanics, every event that can happen does happen in a separate branch of the universe. Every decision, every possibility, splits reality into versions. So in one branch, you went left. In another, right. In one, you stayed. In another, you left. each outcome generates its own timeline. In that view, there are countless versions of you, each one with a slightly different story, and, just as important, each one moving through a slightly different version of time. Because once a branch splits, it becomes its own reality. And time there is no longer linked to time here. Even if it starts the same, it can drift. Tiny changes ripple outward. Events unfold at new rates. Different gravitational pulls, different environments, different choices. All of them influence the flow of time. So yes, another version of you could be living a different hour. They could be further along in a conversation, or years behind, or waking while you sleep, or reliving a moment you've already forgotten. And the longer those timelines exist apart from each other, the more they diverge. We can't prove this. We can't detect those branches. But the math suggests they might be there. Not as fantasies, but as real, independent histories. Then there's memory. Memory gives us the feeling that time is moving forward, that each moment is built on the last. But what if memory were constructed differently in another version of you? What if the order of events were scrambled? What if your mind was shaped to remember things that haven't happened yet, or to forget things instantly? You might not even know you were living in a different hour. You would feel normal. Your sense of sequence would be shaped by the same biology, only rearranged. So now the question deepens. Could a version of you exist in a different flow of time, with a different structure of memory and still be you? Is continuity of identity tied to experience, or is it something else? There's no consensus on this, not in philosophy, not in neuroscience, and certainly not in physics. Some thinkers argue that identity is just an illusion, a useful story we tell ourselves to link one moment to the next. If that's true, then any version of you living in any moment might just be a snapshot. Not a full self, but a single frame. Others say continuity matters, that your decisions, your emotions, your values, they build over time, they accumulate, and that accumulation is what makes you who you are. If that's the case, then changing the hour, changing the flow of time, would affect the shape of the self. In a faster timeline, you might experience more. You might age more quickly, you might burn brighter but for less time. In a slower one, everything would stretch, moments would linger, emotions would hold longer, learning would take more time. Neither is better, just different. Then there's the stranger idea, that versions of you living in different hours might, under the right conditions, overlap. Not physically, not in space, but in pattern. The idea here is that if time can be bent, then there might be places in space-time where different versions of events converge, like folds in a cloth. These moments of overlap wouldn't mean communication, but they might mean similarity, a kind of echo. You might feel something, a sudden recognition, a vivid dream, a thought that doesn't belong to your current context. You'd brush it off. But perhaps it's the pattern of another you, living a different hour, slipping past for just a second. No science supports that idea directly, but the math of space-time curvature allows for strange coincidences, and if identity is just pattern, a set of conditions arranged in a particular way, then maybe it's not limited to one place, or 1 hour. Could another you be living a different hour? Not just in theory, but right now. A version of you paused mid-step, or looking out a window, or halfway through the same sentence you're thinking, and if so, would they feel you? Would you feel them? It's impossible to know, but imagining it shifts your perspective. It reminds you that time is not a single thread, it's a field, a space, one we move through with limited tools, memory, attention, sensation. If we could step outside that field, even briefly, we might see other paths, other hours, other selves, not better, not worse, just living alongside, in a way we're not built to perceive. So maybe the question isn't just whether another you is living a different hour. Maybe the question is, how many versions of you are always doing that? And how many of those hours are happening right now, in places you'll never see? If you keep following time back far enough, through the expansion of galaxies, through the cooling of the universe, through the formation of atoms and light, you eventually reach a moment that doesn't look like anything we've experienced, a time before stars, before structure, before time in the way we know it even had a rhythm. This is the edge of our understanding, a moment that's not really a moment, but more like a transition, the place where time and space as we experienced them first took on their familiar shape. It's called inflation. Cosmic inflation refers to a period of incredibly rapid expansion, not of matter, but of space itself. It didn't happen slowly or even gradually. It happened all at once. A fraction of a second after the Big Bang, the universe ballooned outward faster than the speed of light. Not a metaphor, not a flourish. That's what the physics describes. Space expanding so violently that regions moved beyond causal contact with each other. What had been smooth became scattered. What had been one became many. This wasn't a chaotic explosion. It was more like a reconfiguration, a shift from a high-energy, unstable state to something more ordered. That shift released energy, caused expansion, and created the conditions for everything else to unfold. But here's the part that matters for us. Inflation set the stage for time. It didn't just stretch space. It set the initial conditions for how clocks would behave. If you imagine a universe before inflation, time doesn't tick in any recognizable way. There are no stable particles, no structure, no gradients to measure. There's motion, but not in the form we understand. There's a field, the inflaton field, responsible for driving inflation. But its behavior isn't like the forces we see today. Then inflation happens, and in that moment, or rather in that process, clocks are born. Not clocks like devices, clocks as processes, repeating, reliable sequences of change, the kind of things that let you measure time at all. Inflation ends when the energy in the inflaton field decays into particles. That's what sets off the so-called hot Big Bang. The universe fills with radiation, quarks, gluons, matter and energy locked in a dense plasma. But more than that, it fills with patterns, differences in density, quantum fluctuations stretched across space, turned into seeds of galaxies. All of this begins to unfold on a timeline, a meaningful one, and that's why the end of inflation is sometimes referred to as the beginning of time as we experience it. But what does it mean to say that clocks are tied to inflation? It means that the way time flows now, the way it moves forward, the way it links cause to effect, is shaped by the conditions that inflation left behind. Inflation doesn't just create space, it imprints a kind of order, a baseline, a structure that defines how things will evolve, and evolution is what clocks measure. Think of it this way: a clock is anything that changes in a consistent way. It could be an oscillating atom, it could be a burning candle, it could be the spin of a particle. In a chaotic universe with no consistent rules, clocks can't exist. But after inflation, the universe cools into a form where rules emerge. Constants take shape. Particles behave predictably. Interactions stabilize. And once that happens, the universe becomes readable, measurable, countable. Clocks aren't just instruments we build. They're a reflection of physical order. So inflation, while violent and brief, is what allows time to start ticking in a way we can describe. Now here's where things get strange again. Inflation may not have ended everywhere. In many versions of the theory, inflation is eternal, not in the sense that it goes on forever in one place, but that it keeps happening in different places. Our universe is just one region where inflation stopped, but elsewhere, in other patches of the larger space, it continues, forever spawning new regions, new bubbles, new universes. That means each of these regions, each pocket where inflation ends, could have its own timeline, its own version of order, its own definition of what a clock is. Because if clocks are born from the decay of inflation, and that decay happens in different ways, at different rates, with different outcomes, then the flow of time in each resulting universe could be unique. One bubble might expand slowly, Another might expand rapidly. One might form stable matter. Another might not. One might have 3 dimensions of space and 1 of time. Another might have more or fewer, and in each, time ticks differently, not metaphorically, structurally. That doesn't mean people live in every one. Most bubbles would probably be unstable, hostile to complexity, but the variety is there, and in that variety you find the first true clocks of each universe, ticking according to their own rules. So when we ask if time ticks the same way in other realities, we're really asking how inflation played out for them. In our own universe, we can still see the fingerprints of inflation, the cosmic microwave background, the afterglow of the early universe carries imprints of those first fluctuations, tiny differences in temperature stretched across the sky that match what inflation predicts. Those fluctuations are like a clock signature, a record of how the first moments unfolded. And they're not random, they're statistical, structured. They're what let galaxies form, stars ignite, planets orbit. They're also what set up the tempo for all processes that followed. Without inflation, the universe might be smooth and featureless, or chaotic and unstable. But with it, we get clocks, sequences, evolution, time, in the sense we live it. And if inflation happens elsewhere, those places would have their own sequences, their own initial fluctuations, their own clocks. Would we recognize their time? Probably not. The values might be different. The scales might not match. In some universes, processes might unfold too slowly to notice, in others too fast, but in each case time would be tied to structure, to the way the inflaton field decayed, to the way space settled, to the way energy cooled. That raises a strange possibility. If time is a consequence of inflation, if clocks are born from that process, then maybe what we call now only exists because our patch of the universe cooled in a specific way. Maybe now is local, not in space, but in origin, and that might mean there are other nows unfolding elsewhere, independent, inaccessible, but equally real. From that perspective, the clocks of cosmic inflation don't just mark the beginning of time, they mark the branching of reality, each clock in its own bubble, each tick a new version of how time can be lived. If clocks are born in the wake of cosmic inflation, and if time begins its long stretch from that sudden expansion, then light is what carries the news forward. It's what moves through the fabric of time, carrying information from one moment to the next. In a universe made of events, light is the way we know one happened before another. It defines what we can see and when we can see it. It's not just a signal, it's a messenger of the past. But the more we've looked at light, the way it bends, stretches, redshifts and slows, the more we've realized that it isn't untouchable. It's shaped by the same forces that shape time. And once we begin thinking about other universes, with different shapes and different clocks, we're left with an unavoidable question. Does light age differently elsewhere? To answer that, we have to start by asking what it means for light to age at all. At first, it might seem like it doesn't. Light, or more precisely photons, are said to travel without experiencing time. According to special relativity, if you were somehow able to travel at the speed of light, which you can't, but hypothetically, time would stop. From the point of view of a photon, there's no before and after. It leaves one place, arrives at another, and does not register the space in between. But from our perspective, from the point of view of someone watching that photon move, time absolutely passes. We see it take its journey. We see it stretch if it's moving away. We see it blue shift if it's coming toward us. The light evolves, not in a personal sense, but in how it appears to us. And those changes depend on the structure of space-time. That means light might not experience time itself, but it's absolutely influenced by how time behaves around it. And this is where the question becomes interesting, because in a universe with different physics, a different gravitational landscape, different constants, a different shape of space, light might travel differently. It might stretch more. It might shift in unfamiliar ways. It might decay into other particles, or not decay at all. In our universe, we know that light changes with distance and time because of expansion. The farther a photon travels, the more stretched it becomes. This is known as cosmological redshift. It's not just a matter of movement, it's the stretching of space itself. As the photon moves through that space, its wavelength grows. It loses energy. Not because it's tired, but because the universe has expanded underneath it. So even though a photon doesn't feel time, it carries the marks of time's passage. Now imagine a different universe. Suppose space doesn't expand there, or expands at a different rate. Suppose the constants that define light's behavior, like the fine structure constant or the vacuum permittivity, are slightly off. Suppose the photon's journey doesn't involve redshift, but something else, something we don't have a name for. Would that photon still age? From an outside view, yes, but it might not show it the same way. It might not lose energy the way it does here. Its wavelength might stay fixed, or it might compress, or it might interact with the vacuum in different ways, gaining or losing energy based on rules that feel alien to us. And if light behaves differently, then everything we think of as visual, as observable, would shift. In our universe, we use light to map history. The further out we look, the further back in time we see. We can measure the age of photons by their redshift. We can tell how long they've been travelling. That's how we build our timeline. That's how we piece together the story of the universe, one photon at a time. But in a universe where light doesn't stretch the same way, that strategy breaks down. Imagine a reality where the universe is static, not frozen, but unchanging in scale. Light would still travel, but it wouldn't redshift from expansion. It might still lose energy in other ways, through interactions, through curvature, through exotic processes, but we wouldn't see the same clean progression of red light for older photons. Time there would look different. The sky would not record history the way ours does, and if you lived inside that universe, your tools for interpreting age and distance would have to be completely redefined. Or take the reverse. A universe where expansion happens much faster. Photons would redshift dramatically. Light would age quickly, fading out over short distances. In that case, you might never see more than a few million light years away, not because the light hasn't arrived, but because it lost its energy too quickly. The past would be hidden by physics, not distance. It would feel like living inside a shrinking memory. And then there's the structure of light itself. Photons aren't just packets of energy. They're also carriers of momentum, of frequency, of quantum information. In our universe, they behave in ways we've studied and modelled extensively. But those behaviours depend on certain assumptions, like the constancy of the speed of light, the nature of vacuum, the availability of quantum fields. Change those, and you change the rules. In some versions of string theory or other high-dimensional frameworks, photons might not be fundamental. They might be emergent, a byproduct of deeper structures. If that's true, then in another universe the same structures might not emerge, or they might emerge differently. Light might not even exist as a discrete particle. It might be a wave in some unseen dimension, or a vibration of a more complex field, or something entirely unfamiliar. In that case, what we call light might not be universal at all. It might be local, a feature of our particular corner of the multiverse. And in those other corners, reality might carry information using something else entirely. So would light age differently there? Yes, but not just differently. Fundamentally, in ways we might not recognize as aging. Maybe the word aging doesn't even apply. Maybe it's something more like transformation, evolution, or replacement. In some models, photons could decay, turning into other particles after a long enough time. That doesn't happen in our universe as far as we know, but it could happen elsewhere, under different rules. In those places, light might have a shelf life. It might not survive billions of years, which means history as carried by light would be short. Not because the universe is young, but because the light from its past doesn't last long enough to be seen. That kind of reality wouldn't just change astronomy, it would change perception itself. Everything we see is shaped by light, not just telescopes and cameras, but eyes, neurons, awareness. If light behaves differently, then perception adapts. Maybe it doesn't rely on photons, maybe it relies on something else. Gravitational ripples or quantum pulses or field resonance. And in that structure, aging, both of signals and of systems, would take on a different rhythm. It's also possible that in some realities light doesn't move at a fixed speed. That's been considered in some speculative physics, models where the speed of light changes over time or is influenced by local conditions. In those models, the relationship between time and distance is not fixed. The clock of light becomes variable. And if that's true, then the story told by light becomes more like a puzzle than a timeline. You wouldn't just read the light and know what happened. You'd have to decode it, adjust for shifting speeds, shifting rules. Time would not be written in light. It would be encrypted inside it. Back in our universe, we trust light as our main interpreter of time. We see the past in starlight. We measure cosmic expansion by how much light is stretched. We map the oldest events by collecting the oldest photons. But all of that relies on the assumption that light behaves in certain consistent ways. Take that away, and what's left? A world where time is not visible. Not because it's not there, but because the things that show it, that carry its signature, don't exist in the same form. So when we ask if light ages differently elsewhere, we're not just talking about particles, we're talking about perception, memory, interpretation. And if time exists in places where light doesn't behave the way it does here, or doesn't exist at all, then time in those places would be unreadable. Not absent, but unreachable, still present, but beyond the window we know how to look through. If light is our guide to the past, if it acts as the carrier of time's memory, then what happens in places where light can't reach us? Or worse, places where light can't even escape? These are not hypothetical locations, they're features of our universe, and in them time behaves differently, or not at all. Wormholes, closed loops, gravitational traps. These are the structures where time stops resembling what we think it is. They are not stories or theories, though they've inspired both, but rather the natural consequence of the equations that govern space-time itself, and they remind us that time isn't something you can always count on. Let's begin with wormholes. A wormhole, at its simplest, is a tunnel through space-time, a shortcut, a bridge connecting two distant points. They're predicted by general relativity, and while no one has observed one, the math allows them. In some solutions, a wormhole could connect not just two locations in space, but two moments in time. You could step in at 1 hour and emerge in another, but this only works if the wormhole is stable, and stability is the problem. To keep a wormhole open, to stop it from collapsing under its own gravity, you need exotic matter, something with negative energy density. Not imaginary, but not something we've observed either. Still, let's say for a moment that you had such a thing, that you could hold the mouth of a wormhole open long enough to travel through it. What happens to time in that scenario? It depends on how you move the ends. If one mouth stays still and the other accelerates and returns, much like a twin in the classic relativity thought experiment, then time would pass differently for each side. One would age more than the other, which means that a traveller entering the younger end could emerge in the past, relative to their own departure. Not back to a previous version of themselves, but back to an earlier time in the surrounding world. This kind of shortcut through time doesn't break physics, but it does complicate causality. It creates the possibility of loops, events feeding into themselves, actions affecting their own causes. And once you allow loops, you begin to question the arrow of time itself. In most places, time moves forward. Entropy increases, events unfold one way, but in a loop, direction breaks down. A closed time-like curve, the term physicists use, allows you to travel along a path in space-time that eventually returns to the same point. Not in space, in time. What does that feel like? We don't know. No one has ever travelled such a path. But if you could, you might witness your own past. You might exist alongside an earlier version of yourself. You might even cause the event that led you there in the first place. This is the paradox territory, the domain of bootstrap scenarios, where an object or a person exists only because of its own future. A notebook passed from the future into the past, copied and returned again. A loop with no origin. In our current understanding, such paradoxes don't necessarily violate physics, they violate our expectations, but mathematically they're self-consistent. The only rule is that the loop must close in a way that doesn't contradict itself. You can't change your past, but you can become part of it. That idea leads directly into timelessness, because if time can loop back, if events can exist in closed circuits, then the sense of progression fades. A loop doesn't stretch, it repeats. It has no edge, only motion, and in that repetition, time loses its forward momentum. It's not that things stop happening, it's that happening itself becomes a circle, a repetition that, to the traveller inside, feels like motion, but from outside appears frozen. Now imagine a place where the loop is so tight, so compressed, that the traveller can't distinguish one cycle from another. They move through events, but the events are identical. Thought and memory reset. Experience replays. From that point of view, time isn't moving forward. It isn't even standing still. It's erased, rewritten continuously, a rhythm with no memory. This brings us to the extreme end. Places where even light cannot escape. Black holes. In these regions, gravity is so intense that nothing, not even photons, can escape once it passes the event horizon. From outside, an object falling into a black hole appears to slow down. It never quite reaches the edge. Its light stretches, fades, disappears. Time, from the perspective of an outside observer, seems to freeze. But for the object itself, for the astronaut, the probe, the atom, time continues. It falls. It crosses the event horizon. It approaches the singularity at the centre, where all known physics breaks down. At that point, if the math holds, space-time becomes so curved that direction, duration and location lose their meaning. Time, as a measurable dimension, collapses. Everything points inward. There is no after, no before, just descent. We don't know what happens at the singularity. We may never know, but it represents something critical. A place where time, shaped by the surrounding structure, ceases to function. Not because it's destroyed, but because it has no usable definition. This is the most literal version of timelessness we know. But there are softer ones. In cosmology, some models describe regions so empty, so diffuse, that time has no events to measure, a void billions of light years across with no matter, no light, no change. In such a space nothing happens, no clocks tick, no particles interact. Time may exist there, but it's invisible, not flowing, not stopping, just waiting. And then there are quantum systems. At the smallest scales, time becomes strange. Superpositions blur before and after. Certain quantum gravity theories suggest that time might be emergent, not fundamental. That it arises only when systems become complex enough to measure change. In the deep quantum regime, before space or matter or energy have stable definitions, time might not even exist. It might not be missing, it might simply be irrelevant. So we arrive at a peculiar truth. There are places where time loops, places where it collapses, places where it freezes, places where it waits, and places where it never forms. In all of these, the familiar flow, the seconds we count, the stories we tell, the lives we live, stops being a rule. It becomes a condition, a choice made by physics under specific circumstances. Elsewhere, other conditions exist, some with light, some without. some where events return, some where they do not begin. It's easy to forget when we talk about time, when we measure it, name it, divide it, that all of those markers are inventions, clocks, calendars, ages, anniversaries. None of them are time itself. They're tools we built to help describe something we still don't really understand, something we feel but can't quite touch, something we move through but never quite from outside. The question we keep circling is whether time is real in the same way that space is real, whether it's a direction, something you could point toward, or just a kind of awareness, a sensation produced by memory and change. Maybe both. We tend to treat time as a dimension. We say that space has 3, up, down, left, right, forward, backward, and then we add time as a 4th, a line we travel along. It's a helpful idea. It lets us describe events as locations in space-time. A thing happened here, at this point, at this hour, and in general relativity, that works. It lets us chart orbits, predict outcomes, understand gravity. But there's a quiet detail that often gets skipped over. Time is not quite the same as space. It behaves differently in the math. The sign in the equations is reversed, and that subtle difference leads to some very real consequences, like the fact that you can stand still in space, sit at your desk, lie on the ground, but you can't stand still in time. You're always moving forward. You don't feel yourself moving, but you know you are because the world changes around you. You get older. The stars shift. The sun rises. That one-way motion, that continuous unfolding, is one of the most fundamental features of human experience. It shapes everything we do. But when you look closely, the laws of physics don't insist on it. The equations that govern particles, fields, and forces, they're mostly symmetric in time. They work just as well forward as they do backward. If you took a video of 2 particles colliding and played it in reverse, the physics would still check out. Nothing in the rules of the interaction cares which direction time flows. The math is indifferent. So why do we experience time in one direction? The usual answer is entropy. Entropy is a measure of disorder, or more precisely, the number of ways a system can be arranged. Over time, entropy increases. That's the second law of thermodynamics. Hot things cool down, systems spread out, order becomes randomness, ice melts, smoke disperses, and that increase in entropy gives us the arrow of time. You don't see a shattered glass reassemble itself. You don't see smoke pull back into a cigarette. Not because the laws forbid it, but because it's overwhelmingly unlikely. There are more ways for things to be disordered than ordered, so systems drift in that direction. That drift, that statistical trend, becomes the flow of time we feel. And this is where the line between direction and feeling starts to blur. Because if time's direction is based on entropy, and entropy is just a statistical tendency, then the arrow of time might not be a fundamental feature of the universe. It might be an emergent one. Something that arises when the system gets complex enough, when there are enough particles, enough interactions, enough differences, to make the imbalance noticeable. That would mean time's direction isn't written into the fabric of reality. It's written into our part of it, into our conditions. But what about the feeling? Why do we remember the past and not the future? Why do we see cause before effect? Why do we expect one thing to follow another and not the other way around? Some theories say it's because memory is a process that leaves a trace. When a neuron fires, when a page is written, when a photograph is taken, those are irreversible events. They only happen when entropy increases. So memory only works one way because that's the way physical processes are allowed to unfold. In that sense, our perception of time, the feeling of before and after, is just a reflection of how information is stored. But there's something deeper. Even without memory, we might still feel time. Some people who experience certain neurological conditions, like amnesia or specific kinds of brain trauma, lose access to memory but still report the sensation of time passing. The moment still moves, experience still flows. They may not remember the past, but they feel the present slipping into it. That suggests the feeling of time might not be tied only to memory. It might be something more basic, something tied to attention, to perception, to the act of change itself. Some neuroscientists believe the brain processes time as a continuous narrative. It collects sensory input, evaluates it, and organizes it into a stream. That stream becomes experience, but it's not stored as discrete moments. It's smoothed, like video frames blended into motion. And that smoothing gives rise to the sensation of continuity, of time flowing. If that's true, then the feeling of time might just be a byproduct of how our brains handle change. We don't see the static images, we see the movie. But even this might be shaped by evolution. If you were a creature with no memory, no prediction, no way to sense change, you wouldn't survive long. You wouldn't avoid threats. You wouldn't seek food. You wouldn't know when to rest or when to move. So perhaps time, as a feeling, is something biology built for survival, a constructed awareness, a useful illusion, but not necessarily a reflection of something external. And that raises a strange possibility, that what we call time might be more like temperature, a measure that emerges from many individual motions, but isn't itself a thing. There's no single particle of temperature, it's a pattern, a behavior, and maybe time is the same. Not dimension you move through, but a summary of how things change, a description of the difference between then and now. If so, then asking whether time is a direction or a feeling might be like asking whether music is a wave or a sensation. It's both. There's a structure to it, a pattern you can model, record, replay. But there's also the experience, the sense of progression, the rhythm you feel, even if you can't describe it. And if time is like that, if it's both a direction in the math and a feeling in the mind, then we need to hold both truths at once. Because the universe may not care which way time flows, but we do. We tell stories in order. We age. We hope. We regret. And none of those things make sense without a direction. Asking what time it is in a baby universe sounds like a playful question, something you'd say with a smile, maybe late at night. But when you stop to consider it carefully, it becomes something else, a kind of doorway. Because hidden inside that question is something far more serious, the question of whether time exists at all when nothing has yet taken shape. We often picture the early universe as a hot ball of matter, dense, exploding outward, bright, violent. But that image is misleading. For one thing, it wasn't an explosion in space, it was the expansion of space itself. And for another, there wasn't really a ball, there wasn't an edge. It wasn't fire in a void, it was just energy, uniform, nearly featureless, stretched across a space that was only just beginning to exist. In that kind of environment, can you really say what time it is? Right now, in this moment, time feels stable. You can look at a clock, you can check your phone, you can think about what happened an hour ago and what you'll do tomorrow. But those assumptions depend on a lot of structure. Clocks that work, systems that stay in sync, processes that unfold at a regular pace. In a newborn universe, none of that is guaranteed. So what would time mean in a place where nothing has stabilized yet? At the very beginning, during or just after inflation, everything would have been shifting faster than any observer could track. The inflaton field, which may have driven the early expansion, would still be decaying, releasing energy and filling space with a storm of particles and radiation. There would be no stars, no atoms, no clocks, no observers, just raw energy and expanding geometry. If you dropped into that moment and somehow existed there, you'd find no reference points. Nothing to measure against, no ticking, no cycles, just continuous change. So the first problem is that time depends on difference, on comparison, on a before and after. But in the earlier stages of the universe, the changes are not discrete. They're not measured by systems evolving independently. They're just transitions, one field blending into another, one distribution of energy melting into a new pattern. Still, physicists do assign a timeline to those stages, not by using physical clocks from that moment, but by applying equations that let them estimate how much time would need to pass, based on temperature, density, and particle interactions. In those models, the first few seconds of the universe are mapped with extraordinary precision, but the numbers are retrofitted. They're applied from our current understanding. So when we say this happened at 1 second after the Big Bang, or this happened at 10 or just 35 seconds, we're not describing actual experiences. We're assigning timestamps based on energy scales, based on when things would cool, when symmetries would break, when particles would form. But none of that means there was a working clock. Not in the early stages. So what was time doing then? Was it even moving, or was it only waiting for something to begin counting? One view is that time is always there. It exists alongside space, even if there's no one to track it. In that view, the early universe did have a time, just not a meaningful one. A kind of empty time without markers, not yet useful, not yet expressed, like a track with no train. Another view is that time emerges, that it doesn't exist until there are systems that can evolve in a reliable way. That means atoms, or temperature gradients, or stable configurations of matter. And in that view, the early universe had no real time. It only had change, and not the kind we could recognize. Only when particles began to interact, when energy became matter, when fluctuations became structure, could something like time begin to tick. So in a baby universe, the question, what time is it, might have no answer. Or the answer might depend entirely on how you define the word. Still, even in those early stages, things happened. Symmetry broke. Forces separated. Matter emerged. Those changes took place over intervals, over durations, even if those durations weren't measured. And once the universe cooled enough to form quarks and gluons, to stabilize protons and neutrons, to allow light to travel freely, then real events began to unfold. From that point on, you could place a clock. It wouldn't look like a mechanical object. It would be a process, a repeating interaction, a decay pattern, the kind of behavior that can define regular intervals. That's what physicists often use as the baseline, the ticking of a transition, played out again and again with predictable rhythm. So maybe the better question is not, what time is it in a baby universe, but when does time become useful? Useful for prediction, for sequence, for meaning. The answer seems to be, as soon as systems can begin to store and share information, as soon as changes can leave a trace. In our universe, that started within microseconds, then seconds, then minutes. In those moments, hydrogen began to form, light broke free, the first elements fused. Time, as a measurable phenomenon, was now in place. But there's still a deeper implication hiding in the question. What if you could look into a baby universe from the outside? What if, in this multiverse model we've been considering, a new universe budded off from inflation, one of many, and you, somehow existing in the space around it, could ask what time it is inside? What answer would you get? From your perspective, you might see that universe expand in a fraction of a moment. You might see it mature instantly, or not at all. But from the inside, for the beings that might one day evolve there, billions of years could unfold. They would build clocks. They would study light. They would ask the same questions we're asking now. And that brings us back to relativity. Because time is not absolute. It depends on your frame of reference. It depends on your position, your velocity, your gravity. A baby universe might age slowly from the outside and quickly from within, or the reverse. Which means the answer to the question depends not only on what kind of universe you're looking at, but where you're standing when you ask. Time is not a fixed label you can place on every patch of reality. It's local, conditional, tied to experience. So what time is it in a baby universe? It's the time defined by its own birth, by its own unfolding, by its own clocks, whenever they finally begin to tick. For most of your life, time probably felt like a shared thing. When someone says it's 5 o'clock, you assume it's 5 o'clock for them too. You expect everyone to be moving through the day together. The same seconds, the same rhythm, maybe different time zones, but still part of one great clock. That assumption runs deep. It's how we organise conversations, schedules, holidays, history. We trust that time is moving forward evenly, everywhere. But that's not exactly true. It turns out time is not as universal as it seems. That idea might sound dramatic, but in physics, it's a basic feature of how the universe works. The concept of a single time, one ticking beat for everyone, everywhere, only holds if space is flat and unmoving. That isn't the reality we live in. What we've learned, through both theory and experiment, is that time is local. It's shaped by conditions, where you are, how fast you're going, how much gravity is around you. All of those things influence how time moves for you. That's not metaphor, it's measurable, and it means something that seems simple, like the age of the universe, gets complicated very fast. Start with a famous example, GPS satellites, the ones that help your phone tell you where you are. Those satellites orbit above Earth, farther from its gravity well. They also move fast. Both of those conditions, weaker gravity and higher speed, affect how quickly time passes for the clocks on board. If engineers didn't account for relativity, your GPS wouldn't just be a little wrong. It would drift by kilometers each day. That's because time moves faster for the satellite than for someone standing on Earth. The clocks on board have to be adjusted constantly to match ground-based time. Now expand that idea out. Imagine you're on the surface of a neutron star. The gravity there is far more intense than Earth's. That gravity stretches space-time so much that time slows dramatically. An hour near that surface might correspond to years far away in open space. That's not just a story from science fiction. That's what general relativity predicts, and what's been confirmed in smaller ways through real measurements. So even inside one universe, time is not a shared experience. It's not a blanket stretched evenly over reality. It's more like a patchwork, with some areas stitched tighter than others, some stretched, some compressed. And you don't notice the difference unless you compare. Unless you bring two clocks together and see that they disagree. That disagreement can be tiny, a few nanoseconds, but it's real. And if the structure of space is varied, with stars, planets, black holes, expanding voids, then the flow of time varies too. Now imagine a universe with even more complexity, with stronger gravitational wells, with more movement, with more curvature. The differences would be even more extreme. And now imagine multiple universes, each with their own geometry, their own laws, their own expansion rates. In that framework, not only is time not universal within a single cosmos, it's not even comparable between them. That brings us to the idea of cosmic time. Cosmic time is a kind of idealized clock. It's what we use to describe the age of the universe from a particular frame, one that moves with the general flow of matter. It's like a background average, the time measured by someone sitting still with respect to the expanding universe. But no one actually sits still with respect to everything. Galaxies move, stars orbit, people rotate with their planets, so no one experiences cosmic time exactly. It's a reference, not a shared heartbeat, and the farther you get from that average frame, the more your time diverges from it. That means there is no single now. There is no moment that every atom in the universe agrees upon. Every location has its own clock, its own path through space-time, and the idea of simultaneity, the idea that two events can happen at the same time, becomes flexible. In special relativity, this is shown through something called the relativity of simultaneity. It says that what's simultaneous for one observer might not be for another, depending on how they're moving. Two flashes of light, seen at the same time by someone standing still, might be seen at different times by someone moving past. This isn't just a technicality. It's a foundational truth. There's no privileged frame of reference, no cosmic master clock ticking above it all, just local experiences stitched together by comparison. And that's just our universe. If you entertain the idea that other universes exist, separate regions with different physical conditions, then time becomes even less universal. One universe might expand rapidly, making time stretch. Another might be dense and stable, with time unfolding slowly. One might have no meaningful passage of time at all, no interactions, no clocks, no change. Or more strangely, a universe might have laws of physics that don't even include time as a dimension. A reality built on static states, or probabilistic transitions, or something we don't have language for. So the word time might not even apply the same way in those places. What we call time, continuous change, forward motion, increasing entropy, might be a local feature of our universe, not a feature of reality itself. This raises a problem. How do you compare time between places that don't share a baseline? You can't, really. If two universes can't interact, can't exchange information, can't synchronize clocks, then the notion of comparing what time it is between them becomes meaningless. It's like asking how fast a page is turning in a book you'll never open. The question assumes a connection that doesn't exist. So when we ask why time might not be universal, the answer is because nothing in physics requires it to be. Time is not an external drumbeat. It's a measurement of change, a description of order, a coordination of moments, and all of those things depend on context. Even inside a single room, two clocks at different altitudes will tick at different rates. Even inside one atom, energy levels evolve based on environmental conditions. Even inside a single thought, neurons fire in patterns shaped by chemistry, temperature, history. Time is everywhere, but not equally. And if that's true in our universe, it's almost certainly true beyond it. So maybe what we call time is just the name we give to what change feels like when it's arranged in a way that allows memory and prediction. In that view, there is no universal time, just local times, each unfolding according to its own conditions, each shaped by its own rules, each lived by its own observer. Even if time isn't universal, even if every observer in every corner of space experiences it differently, there's still something almost everyone agrees on. Time seems to go forward. You drop a glass, it breaks, the coffee cools, the candle burns down. Things don't just happen. They happen in a direction. This feeling is so consistent, so basic to our experience, that it hardly feels worth questioning. But if you look closely, you'll notice something strange. The laws of physics, the rules that govern particles, fields, motion, don't seem to care which direction time flows. Most equations work just as well in reverse. If you ran the universe backward, down to the atomic level, the math would still hold. So why does time feel like it moves in one direction? Why do we remember the past and not the future? Why does a cooled cup of tea never heat itself back up? The answer comes down to one idea: entropy. Entropy isn't a force, it's not a substance. It doesn't push or pull. It's a number, a measure of how many possible ways a system can be arranged. When things are neat and ordered, entropy is low. When things are jumbled and random, entropy is high. It's a measure of possibility. The second law of thermodynamics tells us that in a closed system, entropy tends to increase. That's not a hard rule, like gravity. It's a statistical trend. There are more ways for a system to be disordered than ordered, so over time, systems naturally evolve toward that disorder. It's like shuffling a deck of cards. If you start with all the suits arranged and you shuffle randomly, you're almost guaranteed to make the deck messier, not neater. Not because it's impossible to return to order, but because there's only one perfect arrangement and countless messy ones. In physics, that tendency toward higher entropy becomes the arrow of time. It's what gives time a direction. Without entropy, there would be no before and after. Events would just happen, with no sense of progression. But because entropy increases, we can tell which way the story goes. You can watch a movie of an ice cube melting and know immediately which way time is flowing. Run it in reverse, and it looks wrong. Not because the laws of physics are broken, but because the entropy is moving in the wrong direction. This asymmetry, the rise of entropy, is one of the only things in nature that isn't time reversible, and that's why it becomes the quiet guide behind every moment we experience. But what causes entropy to rise in the first place? Why does the universe follow this trend? To answer that, we have to look at the beginning. The early universe, just after inflation, just after the Big Bang, was incredibly hot, incredibly dense, and incredibly uniform. Everything was smooth, the same everywhere. You might think that sounds like disorder, but in terms of gravity, it's actually a very low entropy state. Here's why. When gravity's involved, clumping creates disorder. A smooth, spread-out cloud of gas has lower entropy than the same gas collapsed into stars and galaxies. That's because once gravity starts pulling things together, the number of possible arrangements skyrockets. There are more ways for particles to be scattered inside a galaxy than for them to be spread out evenly in empty space. So the early universe, despite being full of energy and motion, was oddly ordered. That low entropy starting point is what allows entropy to increase. It's what allows time to have a direction. But it also raises a deeper question. Why did the universe start out in such an unlikely state? Why begin so neatly only to unravel? No one has a complete answer to that. It may be a boundary condition, just the way things were. Or it may point to something deeper, something about the structure of time itself. What matters is that from that point on, entropy began to rise. Structures formed, stars ignited, dust collected into planets, heat spread, complexity increased. Not in spite of entropy, but because of it. That may sound backwards, but it's a key point. Entropy doesn't mean things get simpler, it means they become more probable. And sometimes the most probable states are complex ones, filled with feedback, cycles, layers. You're one of them. Your body is made of atoms forged in stars, arranged in patterns that hold memory, conduct thought, enable sensation. And every one of those processes relies on entropy increasing. Your cells burn fuel, releasing heat. Your brain fires signals using energy. Your body maintains order internally by releasing disorder into the environment. You're a local pocket of low entropy, sustained only by the flow of high entropy around you. That's the hidden engine behind life, thought, and time as we feel it. So when you experience time moving forward, when you remember what happened before and wonder what comes next, you're not just following the seconds on a clock. You're riding a wave of entropy. That wave moves slowly sometimes and quickly at others, but it always moves one way, at least here. Because in principle, nothing prevents entropy from decreasing. It's just unlikely. If you waited long enough, truly long enough, you might see particles randomly arrange themselves into order again. But the wait would be longer than the lifespan of the universe, long enough to make impossible a useful approximation. That said, some cosmological models suggest the arrow of time could reverse. Not for us, but in other regions. If the universe expands forever, entropy may keep rising indefinitely. But if it contracts, if spacetime folds back in, some theories suggest time might reverse too. Not as in rewinding everything, but as in entropy beginning to decrease. In those models, beings in the far future contraction would still feel time moving forward. They'd still remember their past, but their past would be our future. Their arrow would be reversed. It's hard to picture, but again, the math allows it. Which brings us back to the question of whether time is a direction or a feeling. Entropy says it's a direction. But the feeling comes from somewhere else. The feeling comes from the trace, the record left behind. A broken glass on the floor, an echo in the air. a thought held in memory. Entropy leaves marks, and those marks are what allow stories to form. Without them, you couldn't tell the difference between a moment and a memory. And maybe that's the real role of entropy, not just to guide the future, but to give the past a shape. So even in a fragmented universe, where clocks disagree and time flows differently in different places, entropy offers something steady. A trend, a tendency, a path from unlikely to likely, from rare to common, from simple to diffuse. It doesn't push, it doesn't speak, but it points, quietly, always forward. The idea of a story seems simple. Something happens, and then something else happens, and then maybe something changes. There's a sequence, a cause and effect, a beginning, a middle, an end. That's how we learn to understand the world, through stories. We tell them about ourselves, about others, about the universe, and almost every story moves the same way, forward, from the past into the future, from once upon a time toward something else. Even if it jumps around, even if it tells parts out of order, it still carries a direction, a flow, like time. So it's natural to assume that stories and time are linked, that one flows with the other, that all stories follow the arrow of time, rising with entropy, shaped by memory, shaped by what's possible and what's no longer available. But is that always true? Do all stories flow from past to future? Or is that just how we've learned to think, shaped by our own direction through time? To explore that, you have to step outside of culture and language and even psychology and ask a deeper question. What makes a story a story? Is it the order of events, or is it the connection between them? Consider this. If you were to watch a video of a leaf falling and then play it backward, it might still feel like a story. A leaf rising from the ground, floating upward into a tree. It's strange, but it has a sequence. Something changes. There's motion, transformation. Is that story less valid than the original? Or is it just unfamiliar? Maybe what defines a story isn't the direction of time, but the presence of change, of development. Maybe it's not about which way it flows, but about whether one moment leads to another, in any direction. But for us, the direction does matter, because memory only works backward. We remember what happened, not what will happen, and that limitation defines how we build stories. We base them on what we know, on what we've experienced, and then we move forward, filling in gaps, imagining what comes next, projecting outcomes. So our stories are shaped by the same arrow as entropy. They grow from structure into complexity, from origin to conclusion, from unknown to known. But what if you weren't bound by that? What if your memory worked in both directions? What if you remembered the future the same way you remembered the past? There's a thought experiment sometimes discussed in physics, a being with time-symmetric awareness, one that remembers what will happen just as clearly as what already has. To such a being, the story wouldn't unfold, it would simply exist, whole, static, complete. There would be no narrative arc, no surprise, just knowledge. That version of a story doesn't need time to pass, it doesn't need anything to happen, it just needs structure. So in that sense, not all stories would need to move from past to future. Some might just be fixed, non-linear, coherent, but timeless. We already see hints of that in some mathematical structures. In general relativity, you can describe entire histories, space-time diagrams that map out every event. They don't happen, they just are. A four-dimensional shape with time as one of its dimensions fully formed. To someone inside the structure, it might feel like time is passing. But from outside, the whole story is already written. So maybe stories aren't about time passing. Maybe they're about perspective. Our brains are built to handle things sequentially, one frame after another. We feel the passage of time because we process moments in order, like pages in a book. But the story of the book doesn't depend on when you read it. It exists all at once, independent of the reader. If time works that way, as a structure, not a flow, then our experience of stories is just one slice through that structure, one path through the possibilities. In that view, the past to future flow is local, not absolute, just like time itself. But what about storytelling as we know it? Why are we drawn to arcs, to progress, to development? One reason is that stories help us understand cause and effect. They teach us what follows what. They let us predict, prepare, survive. From an evolutionary perspective, stories are tools for encoding consequences. This happened, and so that happened. This was done, and this was lost. Another reason is psychological. We need stories to give shape to experience. The world feels chaotic, and stories offer patterns. They give events context. They assign meaning. They help us say, this is how I got here, or this is what that meant. Without stories, we'd still have time, but we might not know what to do with it. And yet, even within human culture, not all stories move forward in time. Some myths circle back. Some rituals repeat. Some narratives loop. Dreams often ignore the arrow of time altogether, jumping between scenes, mixing memories with invention. They still feel like stories, even when they don't follow a timeline. So maybe the requirement that stories flow from past to future isn't a universal rule. Maybe it's a preference, a habit, a reflection of our environment, but not a necessity. In theoretical physics, some models explore the idea of block time, the concept that all points in time exist equally, like places on a map. In that model, the past isn't gone and the future isn't undefined. Everything simply is. The only difference is where you're standing and which direction you're looking. That means the story isn't being written. It's already there. It's your awareness that's moving. So the sensation of a story progressing, of a plot unfolding, might be just that. A sensation, a projection, a feeling of movement through something that isn't actually moving, like a light sweeping across a sculpture. The form doesn't change, but your perception does. And if that's the case, then there may be kinds of stories that don't feel like stories to us. Stories with no beginning, no ending, no change in entropy. Stories that aren't told, just known. Maybe some parts of the universe hold those stories. Maybe we'll never be able to see them, or maybe once in a while we sense them anyway. In déjà vu, in intuition, in moments that feel oddly placed. Whether those are real insights or just misfires of the brain doesn't really matter. The idea they point to is the same, that our experience of time and of story is just one way the universe can be read. If you've ever stood still in a quiet room and noticed the second hand of a clock ticking, you might have had the feeling that time was something outside of you, something separate, structured, indifferent. It keeps moving whether you do or not, but if you've ever lost yourself in a moment, in silence, in thought, in sleep, then maybe you've also felt the opposite, that time wasn't there at all. It's a strange balance. Time is always happening. But we don't always feel it. We measure time constantly, in seconds, minutes, years, but we rarely stop to ask what it is we're actually measuring. We talk about wasting it, saving it, spending it, but we don't hold it. We're surrounded by it, carried in it, shaped by it, and most of the time we don't notice until we pause, until we sit not moving and feel the weight of the present settle around us. Time has direction most of the time. It moves us from cause to effect, from birth to memory. It gives shape to change. It lets us build stories and identities and futures, and yet, for all its motion, we're never outside of it. We don't watch it go by, we ride inside it. That makes it hard to study in a way, hard to look at directly. But we've tried. We've used physics to chart it. We've defined it in terms of entropy and expansion, and the ticking of atomic transitions. We've tied it to the speed of light, to the curvature of space, to the vibration of matter. We've placed it inside equations and built clocks that track it with astonishing precision. And still, there are places where those clocks fall apart, where time stops behaving or disappears entirely. We've found that time bends near gravity, stretches in motion, splits between observers, that it might loop, that it might stop, that it might not even exist at the deepest levels of physics, not as something fundamental, but as something that emerges when systems become complex enough to notice change. We've also imagined other universes, some where time behaves like ours, some where it doesn't exist at all. We've considered timelines that diverge, collapse, fracture, remain frozen. We've wondered what time looks like in a baby universe, in a black hole, in a loop, in a void. And through all of that, we've kept returning to a quiet idea. That time might not be what we think it is, not a line, not a flow, not a thing outside of us. Maybe just a relation between events. Maybe just the name we give to difference. Maybe just the gap between what was and what is. But even if that's true, even if time isn't a force or a dimension but only a pattern, it still carries something with it. A rhythm, a presence, a tendency for things to move forward, or at least to change. And sometimes, in the middle of all that movement, we can pause, not to stop time, not to step outside it, but to feel it more clearly, to notice that the moment we're in isn't just passing, it's arriving. Right now, wherever you are, time is still flowing, cells are dividing, particles are shifting, the earth is rotating under you, and you are somewhere inside all of that, not separate from the river but part of its current, and still, somehow, here, still, breathing, listening, thinking, not behind, not ahead, just in it. And that's the strange gift of awareness, not to escape time, but to notice it, to feel its passing not as a loss, but as a presence. There are people who have tried to explain time as an illusion, as something the brain invents to make sense of change. That may be true, but even if it's an illusion, it's one we live inside, and illusions can still feel real. They can still shape us. They can still be the fabric of our experience. You don't need to solve time to live in it. You don't need to understand entropy to appreciate warmth, or memory, or motion. You don't need to know how clocks work to feel what it means to wait. And sometimes, the most honest response to time isn't analysis. It's silence. It's letting the second pass without interrupting it. It's closing your eyes and feeling the present arrive, again and again, each breath folding into the next. No rush, no conclusion, no ending. Just a long pause in the river of time. Thank you for spending this time with us. Wherever you are now, in bed, in thought, in the middle of sleep's long hallway, we hope this journey through time has brought you something quiet. Maybe a new question, maybe a little stillness. Science doesn't always offer answers, but it offers a way of looking, a slower kind of curiosity, one that doesn't rush to conclusions but sits with the unknown, listens to it, falls asleep beside it. If you found comfort here, if this rhythm suits you, you're always welcome to come back. From all of us at Science for Sleep, rest well and good night.